Stand by.
Today we're cutting a cooler from an RTX 4090 in half. That cooler originally came from one of these. This is a water jet, and it's a high-powered machine that uses grit and water to blast a clean cross-section straight down anything we put under it. Today we're working directly with NVIDIA's thermal engineering team to cut that RTX 4090 cooler in half, but don't worry, no actual boards were harmed in this. And we'll get to see prototypes never before shown to the public to learn more about the real science behind video card cooling, vapor chambers, fan design, and thermal engineering. This interview is heavy in the scientific details, and that's thanks to this guy, Malcolm Gutenberg, thermal engineer at NVIDIA, who didn't hold anything back, including the math, when talking to us.
As you go to bigger fans, pressure isn't proportional to diameter of the 1.6. It's proportional diameter squared and RPM squared.
Okay.
So you actually lose pressure capability.
And it ditches the marketing to really dig into the advanced science of modern computer cooler design. We'll be talking about fan prototyping, blade designs, count, density, fin pitch, cooler analogs for acoustic tuning, and looking at resin cast cross sections of heat pipes and VCs and more. So let's get started. Before that, this video is brought to you by Squarespace. We use Squarespace for our own GN store and juggle complex multi-piece orders all the time with it. Squarespace makes it fast for us to roll out new products with detailed pages full of galleries, videos, and descriptors. It's also useful for your own resume sites, for photographer or project portfolios, or for starting your new small business idea. There's never been a better time to try and start your new business than right now, and we can vouch that Squarespace makes it easy. Visit squarespace.com/gamersnexus to get 10% off your first purchase with Squarespace. Hey everyone, so we have a special video for you today. I'm joined by Malcolm from NVIDIA, and Malcolm, you do thermal engineering.
Yes, sir, thermal engineering.
And he brought all of this really awesome stuff. So we're gonna go through some prototypes of things, I think, right, like fans?
Yeah, we got a bunch of cool stuff here. We got fans, vapor chambers, the new 4090 here.
And do you want to just, we'll tease this, do you want to briefly explain how this happened?
Yeah. So essentially, we took a water jet to our 3090 and our new vapor chamber on the 4090.
Right.
We'll walk you through some of the differences there.
And yes, that'll let us see into the vapor chamber. This is the 4090 itself assembled, and it disassembles into some of these pieces. Not all, there's not this many fans on it. Some of these pieces, but the rest went into designing it. So today's going to be entirely engineering focused. I'm excited because we do a lot of testing of thermals. It doesn't necessarily mean I understand how a company got to the design it got to, and I definitely don't understand all of the different properties in things like fan design, vapor chamber design. So that's what Malcolm's going to help out with. Let's start with these two pieces, and then kind of get into this water jetted thing.
Yeah, sure.
So walk me through, what is this? What am I looking at?
Yeah, so this is probably the earliest version of 4090 that we had. So essentially these were very early acoustic and flow prototypes. So that's initially what we wanted to see, is how the fans performed. Oftentimes the fans are the longest lead time item, and we really want to make sure that, because a lot of things can go wrong in fan design, right?
Is that because you're still kind of figuring out the whole rest of the card as you're working on them?
Yes, sort of that, but also there's a lot of things. We simulate these fans, obviously, very thoroughly, but there's some specific frequencies that you can't necessarily account for, and some have impacts just because of the impedance they're operating at. So it's important to make sure that you know what the sound quality will be before you go and tool a fan and everything. So these are acoustic and flow prototypes, obviously not functional heat pipes in there, but the overall impedance of these is very similar to the final product.
So not necessarily, you're not using it for like thermal load or anything like that. It's just basically for checking noise and just the airflow characteristics.
Exactly. I think there's two of these in the world. One is here, another one in Santa Clara. So
then this leads eventually, after I guess some revision and stuff, to the final design. So this is the 4090 one. I wanted to get to this kind of early in the discussion because it's so cool.
It kind of ties everything together, yeah.
So first, like, I mean, It's a cross-sectioned cooler, right?
Yeah.
Except this is the cleanest cross-section of anything I've ever seen, because I tried to cut a vapor chamber open once, and I used a Dremel, and it basically like liquefied everything. So it just kind of melted. You couldn't see too much into it. And then my next step to try and see into it was to take a drill and step drill it out, and that also was not great. So this, I guess, let's talk through vertically like what it is they're looking at. I'll let you talk about like heat pipes.
Yeah, sure. Yeah. So we got all the, chopped it right in two. We got the vapor chamber here, so that's where you see this gap here. So that's all vapor chamber.
Right.
And it's larger than the 3090 vapor chamber. So you can see the 3090 vapor chamber was about this amount of the card, and then we had the heat pipes on this side. This is the full west side of the card. So the entire area contacting the chip and memories.
Yeah, and to help people with the orientation here, that's GPU contact is in this area if it weren't cut in half. And then I guess you've got memory contact here, right?
Exactly. And then we got 6 heat pipes as well. The interesting part is the evaporator design is completely different than the vapor chamber. So I think this is an area which we spend a lot of time optimizing the evaporator, but the regular user should never see inside the evaporator,
right.
or else something has gone catastrophically wrong. So we actually implemented a new type of wick inside the vapor chamber itself. So essentially, you have two forces in a vapor chamber. You have the evaporation, and you have the rate of evaporation, and then you have the mass flow rate back into the evaporator. And essentially, as soon as the rate of evaporation is greater than the mass transfer rate back into the evaporator, you run into dryout. And essentially, your thermal resistance skyrockets and your thermal performance, well, tanks, I guess.
Yeah, so is that because it is no longer condensing back? Is that what's happening?
It might not have enough capillary force to get back. It could, there's tons of reasons why you could run into dryout. One of the things that's always different with a new generation of chips is the heat flux of the chip. So essentially, the power density in a certain part of the chip, whether it's in a computing workload or a more memory-heavy workload, can light up different parts of the chip.
Right.
And you'll get higher localized heat flux. And there's basically two ways a vapor chamber can dry out. You can either have too much total power and higher rate of evaporation than back to the condenser, but you can also have localized areas of dryout.
Okay, that seems really hard to troubleshoot.
Very difficult, yeah.
Because at that point, I guess for NVIDIA it's a little easier since you have tools to access sensors on the die, maybe.
Exactly, yeah.
So that could help. But I guess maybe some background info there too. So for when you're working on designing these, if you're at a stage where you already have some silicon you can work with, there's effectively a network of sensors across the die. Is that accurate? And then it's stuff like, for a user, you'll see maybe junction temperature or like edge temperature depending on the vendor, or just GPU temperature, right? Like, as if it's all just one thing. And I don't know exactly how if it's just averaged of all of them, but for you guys when you're working on designing it, you can tap into all the different thermal sensors.
Exactly. So we can look at the north-south temperature delta, which usually gives us an idea of how the TIM is contacting the die. East-west as well. We have a ton of sensors, and some are directly in the hotspots, some are in other, processing parts of the die.
Right.
So we have all that information, and that's a great way to check if we have dryout. Basically, if we have one that's way hotter than the average, then something is up.
Right. So why, walk me through combining heat pipes and vapor chamber, sometimes you'll see just one solution on a product. Where do you draw the line when you're going to start leveraging both?
Oh, that's a really good question. So a vapor chamber is essentially just a 2D heat pipe, So it's the exact same principle, but it's basically really effective at both Qmax and obviously spreading the heat. So the overall Qmax of a vapor chamber is much higher than individual heat pipe. If you directly put a heat pipe, really you're limited by the amount of wick you can have to push water back to the evaporator area.
Is wick, when you use wick in this context, are you talking strictly about a physical wick, or are you talking about a physics characteristic?
So like when I talk about wick, it's just this, either sintered powder or on our new one, basically, we noticed that this is the 3080 VC for reference here.
Right.
So essentially, we have these heat pipes touching directly over the evaporator area. And we found that a lot of the condensation happens directly above, because that's where the heat's being drawn out to the east side of the card. So unlike this version, which has sintered powder wick, and basically sintered powder wick is just the median at which it uses capillary force to push water back.
Right.
We used a mesh type wick on the top. So essentially the difference between a mesh and a sintered powder wick is the overall porosity of the material.
Okay, that makes sense.
Porosity is about typically equivalent to the pore radius squared.
Okay.
So as you go to slightly larger pore radiuses, which you have in a mesh, you increase the permeability. And essentially, you allow water to travel right back to the evaporator much easier. And then we still have sintered powder on the evaporator area itself. It can usually be thinner and has a higher capillary pressure than a wick, mesh type wick.
And we'll drop some footage in too where, just to get into internal heat pipe structure is very similar in terms of what you use to wick things. So we have some footage from a factory of how they make heat pipes, and the sintered powder, it just as the name explains, it is literally a powder copper. Right?
Correct, yeah.
And at least for the factory we saw, they kind of dump it into the heat pipes and then just shake them a lot, and then they heat it up. And alternatives like you're talking about with mesh or weave materials.
Yep.
We were trying to get a shot of it earlier. It's really hard to see, but on the 40 series card, I think you were explaining to me that partway down the vapor chamber, you were explaining what it is we're seeing in there.
Exactly, yeah. So it's a little difficult to see. So on the condenser side, we use that mesh type wick with the higher permeability. And essentially, we have a higher flow rate of water back to the evaporator. I like to think about it as like a blower versus an axial fan.
Okay.
Blower is typically high pressure, low flow rate. Axial fan, high flow rate, low pressure.
Right.
So you can think of sintered powdered mesh as more like a blower. Very high pressure, capillary pressure, good water retention in the evaporator area to avoid dryout, good thermal performance in the evaporator. The evaporator area itself is like 80 to 90% of the total thermal resistance of the vapor chamber.
Okay.
So optimizing the evaporator is really the key. So yeah, and so basically axial fan, mesh, blower, sintered powder.
So there's these copper columns in here, and I guess it sounds like NVIDIA changed the design for this generation for 40.
Yeah, so a couple reasons to have the copper pillars at all. One is structural stability. This is incredibly weak, copper. I can bend it with my hand.
Yeah, without the pillars in it.
Yeah, exactly.
Right.
So you need to have, because we do put a lot of pressure with the die on the vapor chamber. And especially since the die kind of does this pumping motion when you heat it up and cool it down. So we put a lot more pillars in the inside, right above the GPU die. But the main reason for it is because essentially the water is condensing directly on top of the evaporator. And we can wick the water directly back down to the evaporator area. So the Qmax of this card compared to the critical heat flux, the point of which the card dries out is way higher on this one.
Not going to be a problem.
Not going to be a problem, yeah. Even if you're overclocking the thing, basically as far as the electricals will take it, it should be able to handle it. So we're pretty proud of the new VC
design. Yeah. How about so the bumps here at the memory contact?
Yep.
That was not on this design. You see it's just a flat plate. This is extremely common. We see this on basically every video card I've ever taken apart. I think I've run into this once or twice, but can you walk me through design decision here?
Yeah, exactly. So you can see it's actually a different notch pedestal on the north and the east, the west, and the south. So basically, we want to make sure that the pressure on the die is very uniform. So we find a lot of the time whenever someone says, oh, this TIM is not good, it's usually just because you have ununiform contact. Yeah. So essentially, we have non-uniform memory around the GPU, and each memory TIM pad provides a force back on the heatsink.
Right.
So typically, if you look at the temperature sensors, let's say you had no balancing, no notch pedestals, and you just kind of let it run, the north can be like, 5 to 10 degrees hotter than the south, just because you have non-uniform TIM contact.
And we were talking too about how some of these components, at least in the past, if not this design, you will sometimes almost use the component as a standoff to just put a pad on it.
Yep.
Not necessarily because it needs the cooling, but the component itself, that is, but because of I guess the movement?
Just to make sure that the pressure is equal. So we'll put it a lot on the south side here to make sure that we have perfect TIM contact on the GPU itself.
Right.
And then, if you do have perfect TIM contact, the total thermal resistance of that, so let's say, for example, you made it infinitely conductive or zero bond line thickness. Essentially, your gain, net gain in terms of the whole card would be like 3 to 4 C.
Okay.
Like this TIM is really good, especially if you have uniform TIM contact.
Is that what this is over here?
No, this is the
PTM
PTM 7900. Okay. So essentially, it can get down to about 25 to 30 microns bond line thickness in the middle, but we have a curved die, so it's slightly larger at the edges. The other interesting thing about this TIM is it's a phase change material, so it'll squeeze out initially, but then it's got enough viscosity when it is liquid to avoid being pumped out. So basically what we do is we run these cards through.
Oh, and sorry to interrupt, but TIM pump out is an issue we talk about in another video. I'll link it below so you can get details on that. I'm trying to define some of the terms as we go.
Yeah, no worries.
So anyway.
Yeah, but basically TIM pump out is the GPU die is slightly curved, and then when you heat it up, it relaxes slightly. So it creates this pumping motion.
Right. And
if you have very liquidy material, it can pump out after few hundred cycles.
Right, sure.
And then
if it's
your thermal performance, especially the hotspot, will get really bad.
Before we jump into fans here, how about this stuff that you've got kind of in resin, I guess? I think I've only seen stuff in resin like this if it's like in a science lab of an insect. So what do we have going on here? This is heat pipes cross-sectioned, I guess.
Yeah, exactly. So there's a bunch of different stuff here. Basically, I did cut these two apart for the video here, but all of this stuff is just random stuff. Whenever we have a problem with a vapor chamber, we just chop it open, see what's wrong. So for example, here you can see the vapor space itself. Now, the vapor space is extremely isothermal usually. Like when you're modeling a vapor chamber, we model, the discrete bits, right? We model the shell, we model the wick, and we model each pillar, and the conductivity we assign to the vapor space it can range, but usually it's like nearly 1,000,000 watts per meter Kelvin.
Okay, right.
It's like effectively isothermal.
Yeah.
All your losses are typically, the biggest resistance is in the wick. You have this like wick and liquid film parallel resistance that dominates the total overall resistance. And essentially you want to maintain that vapor space so you have that isothermal capability. And that's really the reason you use a vapor chamber in the first place. So when we're designing, we usually get CNC heat sinks very far back to make sure that everything's kind of working as expected.
Right.
Especially with the vapor chamber, it can drive a lot of the total thermal resistance. Usually it's probably our second biggest thermal resistance. The first is the airflow, right? Getting the most airflow gets the most benefit.
Right. let's do that. Let's talk about airflow. So these are the final fans.
Those are the final fans. Yep.
What is the high level, like most critical thing for us to know before we get into some of the prototypes about the decisions you made?
These fans are really like, we spent a ton of time this generation making sure that they're absolutely perfect.
Right.
So nothing's ever perfect, but these are by far the best fans we've ever made.
Yeah.
First thing, we used a different bearing type. So previously we used a 2-ball bearing, went to fluid dynamic bearing. Overall, there is some acoustic benefit to going to fluid dynamic bearing. Basically, you miss out on all that metal on metal contact.
Oh, that makes sense, yeah.
But the big benefit is also lifetime. The overall lifetime of fluid dynamic bearing is much better than a standard 2-ball.
Okay, yeah.
So, I mean, the big difference, the blade structure is completely different. And what's interesting is these fans look wildly different.
Yeah,
but
different
if you
sides
flip
of the
it
car
around,
too, right? Okay,
they're
yeah.
almost identical.
Right.
Because the pressure, the impedance of the push and the pull, let's grab this, is actually pretty similar. I mean, we can adjust the impedance almost by changing the fin pitch and, how many fins.
Fin density.
Exactly,
right.
fin spacing. So we found that usually we can find an acoustic optimum point in the PQ curve and corresponding to some flow. Oh, PQ is pressure versus flow rate.
Yeah.
So every fan has a PQ curve, and usually you can find that optimum point, and we're obviously going for very low pressure.
Are you talking about the operating point, basically?
Yeah, exactly. So realistically, these fans are very similar. The push is slightly higher impedance overall because it is blocked by the PCB, and you have to change directions. But the fan geometry is fairly similar. The blade design is completely different than last generation.
These two are, I guess, the comparable, right? And then these two are comparable.
Exactly.
So size obviously different, as we talked about. Blade count different?
Yeah, so a couple things. So first off, size is bigger. So you may think that size is always bigger, but there is an optimum point. This time we were limited by how big the actual card is, so bigger was better. Basically, there's very defined affinity laws for fans. So as you increase diameter, if you keep the RPM the same, flow rate will be proportional to diameter cubed.
Okay.
But if you keep the RPM the same, then it'll be louder by, and there's another affinity law for that one. It's not as simple, though. It's got logs and stuff.
Okay.
So essentially, we could do the math and figure out isoacoustics, what our benefit is in terms of airflow. So essentially, it works out to be diameter to the 1.6. So isoacoustic. So the other thing is, as you go to bigger fans, pressure isn't proportional to diameter to the 1.6. It's proportional to diameter squared and RPM squared.
Okay.
So you actually lose pressure capability, but the overall net benefit in terms of cooling performance.
Sorry, I was just looking over your shoulder at PR over here in the background. I'm going, what's going on right now? Is he saying stuff we can't say?
No, he's up here with my man. I can't do math, I'm in PR.
Flow rate goes up, and more flow rate is what cools the card.
What is it you guys are really trying to identify here? I guess ultimately, as easily said as possible, it's best thermals at a given acceptable noise level.
Exactly,
but when you're actually trying to achieve that, I mean, where do you start, right?
There's
a lot of variables.
There's 100 parameters that you could change on a blade shape, and we try and explore as many as possible. The problem is, unlike the diameter affinity laws, that are easy to spit out and sound smart, the height and the blade number aren't so well defined. So essentially, as you change the thickness or the blade number, you pretty much have to change all the different parameters.
And you're dealing with whatever the heatsink itself is, and so that's why, to the comment earlier of you can't make it perfect. The entire reason that fans are still changing when it seems like one of the most sort of mathematically simple.
Dark Ages,
Yeah. So mathematically, I guess you can do as much as you want to make it perfect, but then you throw all the variables at it, and that's why you still advance over time.
Yeah,
right?
exactly.
Because there's still more to do. So
yeah, and there's some interesting things you can do. You know, now that our simulation capacity is kind of growing and we're simulating more, you can actually incorporate the whole heatsink and then figure out what the interactions are between the heatsink and the fins.
Right.
It's you know,
CFD,
all CFD. It's actually really interesting how you model fans in particular. So in a thermal design, you can just, there's basically 3 ways to do it. One, you can just put the PQ curve in and put no blade parameters. That's the least computationally expensive. Just slap it in there, see if it's good, you know?
Yeah.
Then the second way I find really interesting is basically you put the actual blade geometry in there, and you, instead of rotating the fan, you rotate the air around the fan.
Yeah.
So it's called a moving reference frame, and it gives you a pretty good idea of the overall airflow. But what we've been able to do this generation is do a full sliding mesh simulation. So essentially it's a transient simulation, and you do a moving reference frame for every like 1/10 of a rotation, and do or 1/10 of a degree of rotation.
What I'm hearing here is NVIDIA is its own customer for this type of stuff. If you're for computational power to do the simulation, right? Because it's a lot of.
It's cool working for a company with like infinite computing resources, you know? Yeah, you can like specifically look at different frequencies and stuff. So let's say you get a fan back and it's like, oh, 800 hertz is really bad. You look in and contour where the, you know, high acoustic levels are.
Right. There's a little more we're going to talk about too in a separate video, I think. So we'll save this for the next one. But talking about like compression of the thermal pads and stuff like that, and there's a couple other topics along the way we'll get into, especially with some of the TIM choices and the electrical. So for now, I think probably at least most of you have learned something interesting. But write a comment just like you've done in the past when we've done these types of engineering discussions. Let us know what aspect you were most interested in. And thank you very much, Malcolm, for joining for this.
No problem. My pleasure. Very cool card.
Yes. It was great to learn about, and you'll see more in our testing. So check back for that. Thanks for watching. We'll see you all next time.